Hello and welcome to the last part of the last lecture of this class, and we're going to talk about heuristic feature analysis. And in some cases, those heuristics are desirable because they allow us to perform computations a lot more rapidly. And I also want to discuss them because sometimes we might have really good intuitions, and it turns out that those intuitions may only tell us part of the story. So let's start with something very simple, namely sensitivity analysis. So the first sane thing that you might consider doing if you try to, look at, influence functions is to say, well, let's actually just backprop the output through the input, and then I look at, how much the output changes if I perform a slight perturbation of the input. So in other words, if this is my function here, then there, a Taylor expansion can easily be had by taking its derivative, and this is now my local linear approximation. Okay, and the really nice thing about it is that with deep learning frameworks, I just go and backprop with regard to the input rather than with regard to the weights. I get this mostly free, and voila, I actually have some sensitivity measure. At least so you would think. The trouble is that this often doesn't work terribly well because you have things like ReLU or other clipping functions that obscure the influence. And you get really weird results. Furthermore, as said, just looking at the gradient doesn't really tell the full story because you want to know by how much x changes. So basically you want to calibrate. And there's actually a nice hack by Bach et al. And they basically just use gradient times input. And well, that works a little bit better than just using the gradients only. But to illustrate what the problem is, let's say we have some function I1 plus I2, and I just take the ReLU of 1 minus I1 plus I2. Then what will happen is that if the value is in the saturation part, then the gradient vanishes and then I basically have no influence. But that clearly doesn't make a lot of sense because this would just be arguing that if their value is really large, then their value doesn't matter, and only if it's small it matters. Well, it's part of the story. And by the way, here's another example where we just have a simple ReLU, and we would basically get that the gradient just so happens to be the step function, right? So this term here. And so gradient times input smoothes things a little bit, but basically we have this rather precipitous drop here. So you can go and, go through some decent amount of literature to, get something in this context. So there's this paper called DeepLIFT, and it goes through about 3 to 4 pages of how to fix that problem. And these are, well considered and necessary pieces of reasoning. But here's really what happens, right? So let's say we are on that location here, and I want to find, or rather we sit here, and I want to find the influence, and my reference term is here. Then rather than just, saying that, well, the gradient is 1, or here the gradient would be 0, what they do is they basically switch to finite differences and they perform this approximation, and so they get a more appropriate or more intuitive representation of what's going on. So that's what DeepLIFT does. It, in general, just looks at an entire deep network, looks at the various layer types, and then for each layer type, it discusses on how you can go and approximate things, and it goes into a fairly elaborate amount of detail into splitting positive and negative branches in order to address essentially finite differences in the face of a maximum or minimum. I think there's probably a paper that's worth to be written that tries to simplify this and essentially get to the same type of rules without having that splitting. But since they've already implemented it, well, you might as well use it. But basically, the good thing is, if you do that, you can use, well, backprop to compute the score. So let me just explain a little bit what happens. So they as before, say, well, we want to have a difference decomposition. In other words, the changes in the various coordinates should then affect an appropriate change in the overall function value. So therefore, those terms C, delta xi, delta f. So in other words, those we used to call, we called them before influence functions phi I of x. They need to add up to explain the full difference. And then what they do is they go and, compute the gradient effectively. So they basically take, C divided by, okay, and actually that's a typo here. It shouldn't be delta f, it should be delta xi. So basically that relative change. And so what you can do is, if you use backprop, you can then go and, write out those change terms as a product, and then we're actually in a good situation. Because now, once you have these product terms, you can backprop them nicely. So there's a lot more that you can do with regard to, feature explanation. So there's this thing called guided backprop. It's fallen a little bit out of favor because the other terms are a bit more statistically well-founded. There's something called kernel SHAP, which tries to make the appropriate approximations. And then, as said, probably one of the most exciting areas right now are applications to text and images, because they need to combine larger components, because just saying, well, this is Alex because the third pixel from the top looks like him, doesn't convince a lot of people. Likewise, for text, you need to deal with it. But what we really, really would like is, we would like to explain why something happens, right? This is really a very, very poor man's version for doing causality. But the trouble is, causality is hard. You need to understand the statistical problem, and yeah, deep learning frameworks don't support it quite so easily. So that's why we have a lot of feature explanations. Now, there's a lot of really good work, and I've gone, through, some of the relevant ones. So the Sundarajan and Rajmi paper, that's the one with the integrated gradients, and also explains, the different Shapley values. The Lime paper is the one by Ribeiro et al. The Lundberg and Lee paper introduces SHAP. The Yansing et al. Paper explains why you when you should take conditionals and when not. Then, the Sri Kumar et al. Paper, that's, the, backprop hack. And by the way, if you want to know more about Shapley values and all of that, Kevin Layton Brown has a really nice deck of slides, and I've shamelessly stolen the Micronesian example from him with some adaptations to the actual number of members of parliament. Be careful that towards the end there are a few typos in the slides where inequalities go a bit differently. I mean, that happens to everybody. You've probably seen some typos on my slide deck as well, so don't be too harsh on him. But if you see something and do a double take, well, probably that double take's appropriate, but these are really great slides. You'll learn a lot. So I think what we covered today quite extensively was issues of explainability, what kind of options we can pick, how to deal with conditional terms, then, the more modern breed of axiomatic approaches to give us features, and also a couple of heuristics, because sometimes stuff is just slow if you don't do it efficiently. And with that, that's the end of the class. It's been a pleasure. I hope you learned something from that. And if you do, please enjoy it, use it reasonably, and teach others. And, well, help us make it better. Okay, thank you very much, and good luck.